Okay, well, why don't we get going then? So yeah, well, thanks very much for the invitation to talk at this event. And so I'm actually, I guess, have two different hats. So I also have a position at UCL in the Mullard Space Science Laboratory, which is essentially a physics department. A lot of my academic research is focused on what people call astrostatistics often, so combining statistical and machine learning type techniques for studying problems in astrophysics. But what I'm actually going to talk about today is work that we've done in a slightly different capacity. So this is in a startup company called Kaganova. And I've listed here the people who have basically contributed to this work. This is really mostly developed by Oliver Cobb and Chris Wallace at Kaganova. And then a number of others as well, some of whom I think are on the call. A number of these are actually UCL students who did internship placements at Kaganova at one point or another. So I realize it's somewhat awkward in this current environment to have all these kind of Zoom meetings and Zoom talks. It's also more difficult for me that I can't, I'm not in front of you and able to see, if people actually are following what I'm saying. So I would encourage you, if you have questions throughout the talk, just unmute your microphone and shout out. I'm very happy to kind of take questions as we go. And if you're happy to, I would also suggest maybe like putting a video on. If we can always turn these off if we have bandwidth issues, and of course no obligation if you're not comfortable with that, but if you are, by all means turn your video on, and it just helps me also just get an idea of if what I'm saying makes sense to you guys. So yeah, let me get going then. Basically I'm gonna so the title of the talk is geometric deep learning on the sphere, and some particular work we've done on efficient generalized spherical CNNs. But I'm going to start off much more general than this, and generally discuss the importance of symmetry and actually connections with physics in deep learning. So as I mentioned, I'm actually based in a physics department, but a lot of my research kind of straddles physics and other domains. And then that'll actually motivate, constructions of CNNs for spherical data, which it turns out is really common and quite prevalent. And then I'll kind of overview some of the recent methods for constructing CNNs on the sphere, and then generalizing these, and again reviewing some recent work in this area before discussing some recent developments that we've contributed in a recent paper as well, before finishing up with some numerical examples showing the effectiveness of these kind of techniques. So to start with, I just want to kind of take a step back and think a bit more broadly about the role of symmetry in deep learning, and really connections between physics and deep learning. So in physics, we're really trying to understand the world, often by taking an approach where we model things from first principles. But the general goal is either to construct generative models or to do inference, often with a model in mind. While deep learning, we're often doing a very similar kind of problem, very similar end goal, if you like. We're really trying to understand the world, usually through generative models and inference techniques, but the way we go about this is often quite different. And it's often based more on learning informative representations or, of our data, essentially, or the processes that give rise to our data. So clearly there's a lot of similarity. There's also significant difference, but I really think there's a lot, because we're effectively trying to solve the same end goal, there's a lot physics and deep learning in particular can learn from one another and can leverage from one another. And a lot of my research is on exploring this kind of connection. So in this talk, I'm going to focus more on how ideas from physics can be integrated into deep learning type of approaches. But in other works, often we're considering the reverse direction. And so, really we're trying to complete a feedback loop here. But for the remainder of this talk, I'm really going to focus more on deep learning itself and with some motivating principles from physics that can help design deep learning methods, essentially. And in fact, it really turns out that this kind of approach, the integration of physics into machine learning techniques, was really one of the key factors that drove the deep learning revolution. And I'll discuss what I mean by that in a little more detail in a minute. So physics really, is often called the study of symmetry. So this is Steven Weinberg, a Nobel laureate who won the Nobel Prize for connecting basically the weak nuclear force and electromagnetic force. And, really, it was because of symmetries that, led him down these developments. And, he's quoted as saying, symmetry here is often the key to nature's secrets. And, others have also, there's some famous quotes around the fact that, physics really, when it boils down to it, is a study of symmetry. And this is what becomes critical. And these are the kind of principles that can also be integrated in deep learning approaches. So let me elaborate in a little more detail what I mean here. So typically in everyday life, when we think of symmetry, we'll think of mirror symmetry. That's maybe the most common type of symmetry that comes to mind. Here we've got a photograph of a mountain reflected in a lake. If we flip this photo up and down, it looks very similar. Okay, we don't have perfect mirror symmetry here, but nevertheless, this is the kind of symmetry that we're often very familiar with, and is the thing that usually springs to mind when people think of symmetry. Another quite common form of symmetry is rotational symmetry. So here we've got a playing card, the jack of spades. If we pick it up and rotate it around, if we rotate it the right number of degrees, we can basically get something that that looks the same as what we started with. So again, we've got some kind of rotational symmetry here. So I guess these are more the kind of everyday ways that we encounter symmetry, and typically what people most think of when talking about symmetry. But in physics, we typically mean something slightly different. We usually consider continuous symmetries, and we'll say a system is symmetric or invariant in the sense that it doesn't change to some kind of continuous transformation. So basically, if we transform the system somehow, it's effectively laws that govern it, effectively the mathematical equations that describe its evolution don't fundamentally change. So a very common form of this kind of invariance is spatial translation. If we have some system here and we pick it up and move it over there, that's not really going to change its internal properties. And so many systems are often spatially invariant. It doesn't matter where in space they are. A lot of systems are also rotationally invariant. So again, if we rotate the system some particular way, it doesn't change its fundamental properties or its evolution. And then the final quite common form of invariance is time translation invariance. So if we look at a system at a particular point in time, or we look at it, say, at another later point in time, if we were to just, in a sense, kind of shift that time coordinate, again, in many systems, that doesn't change the evolution of the system itself. So these are the types of symmetries we usually talk about in physics, these kind of invariants to these continuous symmetries. And these symmetries actually go very deep. In a sense, these are the kind of properties that they're at the heart of a lot of physical laws. So it actually was shown by a mathematician called Emmy Noether around the early 1900s, that for every continuous symmetry of the universe, there exists some kind of conserved quantity. And similarly, the reverse, for every conserved quantity, there's some kind of underlying continuous symmetry acting on the system. And so symmetry really is at the heart of physics. You know, if you study physics at high school or since, you probably come across these principles of conservation of momentum, or conservation of angular momentum, or conservation of energy. Often these are taken as, quite, fundamental laws of physics. But really, where do these laws come from? Well, what Noether's theorem basically says is that these underlying laws actually come from some deeper level of symmetry in the system. And it's translational symmetry that gives rise to the conservation of angular momentum, or rotational symmetry that leads to the conservation of angular momentum. So it's really symmetry, again, that is at the heart of all these physical laws. Interestingly, in Newtonian mechanics, we think of energy as being conserved. And it was shown by Noether that this corresponds to a kind of time translational symmetry. Actually, energy is not conserved in general relativity. And that is also because we no longer have this time translational symmetry. Time is in fact relative in GR. So we can see that these kind of symmetries are really at the heart of physics. And if you like, they're actually responsible for many of these kind of fundamental laws of physics. So in some sense, symmetry is the underlying foundation. And that we can leverage in deep learning models. So encoding symmetry in deep learning, really gets to the heart of kind of capturing some fundamental properties about the underlying nature of our world. I mean, I'm talking here more specifically about, computer vision or image type analysis approaches where, really we're trying to capture some kind of physical properties about our world. And so in that sense, really, this was a key factor that drove the deep learning revolution, which, one of the key starting points in the early 2010s was the advent of these convolutional neural networks, CNNs. And CNNs really at that time resulted in a step change in performance. And really what was at the heart of that is this convolutional structure of CNNs. And that structure captures translational symmetry. And so it's really by capturing this underlying translational symmetry, this kind of underlying, if you like, fundamental property of our universe, that was one of the big reasons that led to this step change in performance. So let me go on to just explain in a little bit more detail what I mean by CNNs somehow capture this translational symmetry. And what I really am talking about here is something called translational equivariance. So equivariance is really just this property where, in a sense, you can reverse the order of some operation relative to a transformation. So here I've written this mathematically. We have some operator A, which might be some kind of convolution or constructing some kind of feature map. And then we have some translation T here. So equivariance to this transformation is really just saying that if we transform the signal after application of the operator, so as we've done on the left here, it's equivalent to doing the transformation first and then applying the operator for all of these possible symbols F. So let me illustrate that diagrammatically. Here we have quite common what are called commutative diagrams, where you can start in some space X, you can apply this operator A, and then you can do some translation after that. Equivalently, you could do the translation first and then apply this operator, and that will get you to the same result. So there's kind of two routes to the same result. And this is really what's known in this property of equivariance. And often we talk about translational equivariance, which is the property that CNNs in particular exhibit. So here, getting a bit more concrete now, if we see an image of a cat here, we could have some mapping in our CNN to compute some feature map, which is this mapping A. And then we can translate that feature map. And so now we've moved everything kind of up and to the right. Alternatively, we could have translated the image itself first and then computed the feature map. And that will give us the same result. So this is what is meant by this notion of translational equivariance. And this is really one of the key properties that make CNN so effective. Effectively, we're imposing some inductive bias in our deep learning model. In this case, equivariance to some kind of symmetry transformation. And because we're encoding that in our model, it allows our model to be learned in a much more principled and more effective manner. And we're, in some sense, capturing the underlying physical understanding of the generative process. Did someone have a question? No? So this is what invariance is. Why is it important? Well, in some sense, this means that if we have a pattern in an image, say, we only really need to learn how to represent that pattern. We're not sensitive to where that pattern is. Clearly, if we had to learn a pattern in all possible positions, that would be a much more challenging scenario. So the idea is fundamentally we represent that underlying pattern once, and then because we've encoded this type of symmetry into the model, we can then automatically recognize all transform scenarios. So here we have a picture of the cat's in the center, but really our model is still going to be able to recognize the cat in the top right, even though the cat happens to be in a different place. And we don't need to, our model doesn't need to learn, how to represent cats in different places. It just needs to learn how to represent cats. And so that's really the key advantage of encoding this translational equivariance, and one of the key reasons why CNNs are so effective. So let me move on to spherical CNNs now. And really, we're going to see what the analog of this translational equivariance is in the spherical setting and how we can go about encoding that. But before we do, let's just consider, well, why are we actually interested in this particular problem? Turns out data on the sphere is very prevalent. It's actually quite widespread. It's not always obvious, but in many scenarios, we recover data on the sphere. And I'll come to some more examples of that in just a second. And really, we want to extend the effectiveness of deep learning techniques to these types of data. And to be able to do that, we really need to be able to encode the symmetries of the sphere and of rotations into our models. If we just pick up planar methods, they're just not going to work. And I'll go into more detail on that in just a second. So data on the sphere arises in all sorts of applications. Of course, there's the obvious case where you're maybe looking at a planet and looking at data over the whole surface of the Earth. Clearly, that's spherical data. But actually, you get spherical data in all sorts of problems, medical imaging problems. For example, in diffusion MRI, you're considering diffusion of water molecules and the direction that water travels. And because you're looking at directions, you're basically looking at data on spheres. And, in each voxel, if you like, you're looking at a kind of spherical representation of the data. So I'm not going to go through all of these examples, but there's very broad set of applications where these types of data arise. Just to elaborate this in a little more detail for a couple of applications that I'm particularly interested in, one of which is in physics, studying what's called the cosmic microwave background, which is the relic radiation from the Big Bang. And by studying this radiation, we can learn a lot about what happened in the very early universe. So typically we send a satellite up to space, we take observations over all possible directions. So we're making observations on the celestial sphere, and we record this cosmic microwave background radiation that we go on and observe. So because we're observing over angles, again, we basically get data on the sphere. Again, in virtual reality, often we have now these what are called 360 cameras, where you take a full panoramic image or video. And again, you're observing over all directions. And so you get images and videos defined on the sphere. So really, we want to apply AI techniques that, as I'm sure you know very well, have been hugely successful in the analysis of standard 2D images and videos and in general computer vision problems. We want to extend these techniques so they can work with spherical types of data. Well, why don't we just pick up existing Euclidean CNNs, planar CNNs, and apply those? We could, in some sense, always project the sphere to a plane and then just use planar techniques on the plane. Certainly, that is something you could do, but that doesn't work very well. So in this projection I've shown of, can you see my mouse cursor? Just someone either give me a yes or a nod. Yep. Okay. So here we've got the globe of the Earth, and we've projected that onto a plane. And of course, this introduces distortions. If you look at Greenland, for example, Greenland on the globe is less than 1/10 of the size of Africa down here. But if you look at the projected map, Greenland looks almost the same size as Africa. So clearly, there are massive distortions there. And with this particular projection, as you get further away from the equator, the distortions get larger. Antarctic here looks absolutely massive, right? So using some form of projection breaks the symmetries and underlying geometric properties of the sphere. And in fact, we chose one particular projection for that previous example, but this is the case no matter what projection you choose. There's no projection of the sphere that can preserve both the shapes of objects and their sizes. This is just a known formal mathematical result that this type of projection just doesn't exist. It's just not possible. So in that sense, distortions are always unavoidable. So we'd like to consider signals defined directly on the sphere. We'd also really like to encode some idea of equivariance to standard transformations. So what is the analog of translation in the planar setting on the sphere? Well, it's basically a rotation. Now, rotating the sphere, essentially changing our coordinate system, if you like, or changing our viewpoint, is now just a rotation on the sphere. So whereas planar CNNs typically encode this translational equivariance, on the sphere, we want to encode rotational equivariance. And this diagram just illustrates why we really need to treat things natively on the sphere to be able to do that. So rotational equivariance is not captured if you projected a spherical map to a plane and applied planar networks with translational equivariance. So here I've got just past of the Earth, South America here, we rotate it to the South Pole. On the bottom row, we consider a planar projection of this. And so again, we have South America in the center here. And now we've projected the image above into this planar map. And you can see that this is very different to just translating South America. Translation on the plane does not capture properties of a rotation on the sphere. And so in general, even a rotation on the plane is not going to capture a rotation on the sphere. So really the key point is we have to treat these data sets and these signals natively on the sphere, and we need to build CNNs defined natively on the sphere. Incidentally, I'll also just comment that at UCL, actually, some work has been done to develop what are called harmonic networks, which do capture rotational equivariance to planar images, because even in the standard planar settings, that lack of equivariance to rotations can also be problematic. So there's some very interesting work done by a number of people at UCL on this topic as well. But again, they're concerned with planar images, whereas here, we're really focusing on spherical data now. So just before we jump into how spherical CNNs are defined and work, there's another approach we could consider instead of doing that. So you may be familiar with this general concept of geometric deep learning, and geometric deep learning is often based on graph type representations of data, and now doing deep learning with graph representations. So we could build a graph representation of the sphere, and we could then just pick up graph type CNNs and apply them to spherical data. But again, this discretization and this kind of graph representation doesn't capture the underlying continuous symmetries of the sphere. So this graph type representation breaks these symmetries and the geometric properties of the sphere. And because of that, these approaches are also not able to capture rotational equivariance fully. So basically, we really need now to construct CNNs directly on the sphere. There's some subtleties when working on the sphere compared to the planar or 2D, the standard kind of 2D images that we're all familiar with. And that is that it's very well known that there's not a way to regularly discretize the sphere. So we can't, for example, so here we've got an image of a sampled sphere, and again, another one rotated at a different point. But if we overlaid these, clearly the samples don't line up. And in fact, this is not just a property of this sampling, it's for all samplings. There's no way to discretize the sphere such that we can then rotate images on the sphere, say, or these sample positions and have them line up. And we are able to do that in the 2D setting. If you take a 2D image with pixels, you can just move everything 1 pixel across. Okay, maybe there's a boundary effect that you want to take account of, but if you just move everything 1 pixel across, then all the pixels line up again. That property just is not possible on the sphere. So it really motivates a different type of approach. This is a fundamental challenge in constructing CNNs on the sphere, is that, working with a discretized sphere directly, it's not possible to strictly capture rotational equivariance. So we need to consider alternatives. And basically, the way we get around this is by considering the Fourier representation of our data rather than just it in the image domain. So, much like in music, looking at, with music, you can consider it in time domain, but you can also look at its Fourier spectrum and can see if it's made up of low frequencies and bass or higher frequency content. So again, we can consider the Fourier representation of spherical data, and that gives us access to underlying continuous representations, which in turn means we can encode these continuous symmetries like equivariance. So I think, I've spent quite a bit of time there just kind of setting up the scene and motivating the background. Let me now kind of dive into a bit more detail on how CNNs on the sphere are really constructed. And I'm essentially going to review a couple of excellent works by Cohen and collaborators and Estevez and collaborators that appeared a couple of years ago. And the general idea here is we take the analog of what's done in the Euclidean setting, but we do it on the sphere. So we have convolutions on the sphere, which I'll come on and describe in just a minute. And then we have standard kind of nonlinear activation functions, which are typically pointwise nonlinear activation functions like ReLUs, for example. So I'm going to briefly just talk about these particular types of constructions. Just as an aside, I should also just mention that there are alternative real space constructions. I cite a few papers there, but these, because of these challenges we discussed with discretizing the sphere, these constructions do not exhibit rotational equivariance. So I'm not going to focus on them any further in this talk. So just to kind of set the scene, I just want to define the kind of coordinate systems we're going to use. So we're going to consider signals on the sphere. So really now we just represent that by spherical coordinates theta and phi. But we're also going to consider the space of rotations, and that's characterized by what's called the rotation group, or SO3. This is a special orthogonal group of dimension 3. And here really we're just characterizing the space of 3D rotations, which we often parameterize by the Euler angles alpha, beta, and gamma. So it's a 3-dimensional space now. Because we're considering rotations, we need to consider, in a sense, the space of rotations, because fundamentally we want to capture this notion of rotational equivariance. So firstly, we need to formally define, like, how do we rotate a function on the sphere, or indeed a function that could be defined on the rotation group, SO3. And really, this is a pretty standard approach. I've written it down here, but we can illustrate this graphically. We want to consider some rotation of some function by a set of Euler angles denoted by rho here. Well, what we do is we basically look at the original. So say we wanted to work out what the sample should be at this point here, where I'm pointing to the Andes in the rotated one. What we do is we apply the inverse rotation. That would take us, say, over to a point here. And then we go and look up in the original signal what pixel values occurred here, which is the Andes. So we look up that value, and now we put that at this kind of point on the rotated function. So this is all this equation is saying. We basically kind of, it's really the analog of if we're doing a translation as well. We look things up at the inverse translated point. So this tells us how to do rotations on the sphere. Now we also need to do convolutions on the sphere. So I've got somewhat complicated equation here, but if we kind of dig into it a bit more, actually, it turns out it's pretty simple. The convolution on the sphere is really just very similar to what we do in the Euclidean or in the planar setting. Essentially, it's the projection of our signal of interest F onto a rotated filter. And that's, all this equation here is saying. But we can also represent that graphically. So here's some data F, our Earth map. And now we're basically just moving the filter around. We're rotating the filter and we're projecting the Earth onto that filter. And that's now giving us the output of our convolution. So it's really, again, just the analog of what we do in the Euclidean setting. In practice, however, we compute this slightly differently to avoid these discretization problems that I talked about before. This convolution is computed in Fourier space. So again, I don't want you, don't need to worry about the details of these equations, but I just wanted to give you a flavor of some of these details, and so we can point to some of these terms as well. So here again, basically the Fourier transform on the sphere is what's called the spherical harmonic transform. We project a signal onto it, essentially, if you like, causes or sine type functions on the sphere, which are plotted on the top right over here. So this gives us our Fourier representation. We also need to do the same thing for signals defined on rotations, on the rotation group. This is often called the Wigner transform. And it's, again, we're really just decomposing something into a particular basis on the sphere. This is 3D. These 3 Euler angles encoded in rho. So we have 3 indices, L, M, and N. But really, we don't need to worry about these details. I would just denote that we typically represent these Fourier coefficients by f hat with the L index denoted. And that means that this could either be the sphere or the rotation group. We use this kind of simplified notation. Now, so actually, before we go on, I guess just to set some terminology, our basis on the sphere is what's called the spherical harmonics. So we have these YLM spherical harmonics, and we have these Wigner functions, these big D functions in the rotation group. So a rotation of a signal, as we saw before graphically, and that equation defining it in the spatial domain can also be computed very easily in the harmonic domain. And it's really just, in some sense, a kind of multiplication with this Wigner big D function. And then the convolution, again, can also be computed efficiently in harmonic space, essentially as a product of terms or matrices. So again, I don't really want you to worry about the details of these equations, but just the point is that we represent things in harmonic space. These things we can now compute efficiently, but also very accurately because we've eliminated all pixelization type effects. Now, let's come to this idea of equivariance. Remember, with spherical CNNs, we want to capture rotational equivariance. So just like we had for the planar setting, we can achieve this with a spherical convolution. So here, A here now represents the spherical convolution. So we can do the convolution first and we can rotate, or we can rotate the Earth first and then do the convolution. And it gives us the same thing. So again, we've captured this rotational equivariance property, which is absolutely critical to the effectiveness of CNNs built on these types of operators. So what's typically done in these kind of spherical CNN approaches is, of course, we also need some kind of nonlinear activation function in a CNN. So typically what's done here is a pointwise activation in the real space representation. Because everything's pointwise, if you're just doing thing a point at a time, if you then rotate it, again, you get this equivariance property. If you do something on a point and then rotate it, it's the same as rotating that point and then doing the operation. That is the case in the continuous limit, but again, because we have this challenging scenario with discretizing a sphere where there's no perfectly regular way of doing that, in practice, these pointwise activation approaches are not strictly equivariant. And doing some numerical experiments to demonstrate this. Basically, we've started with some random test signals, and we've computed the two routes through that commutative diagram and then compared any error. And we've done this lots of times with simulations. And we see that the error we get, the relative error we get with convolution, so these are the spherical convolutions or convolutions on this rotation group, of order kind of 10 to the minus 7. This is all with floating point arithmetic. So basically, we're getting to kind of floating point machine precision. But if you look at the same test using a ReLU, then you get about 0.3 or 0.4, so about 30 or 40% error there. So clearly, you're not capturing that strict rotational equivariance, which then is going to hamper the performance of these types of approaches. Nevertheless, this is effectively the approaches developed in some of these earlier and very seminal works in this area by developing these spherical CNNs. And it's nevertheless found in practice that despite this imperfect equivariance, these models often actually work very well and do in fact maintain a reasonable degree of equivariance. So this is really, I guess, the standard spherical CNN type approach. Basically, what we went through is, really we're replacing compared to the planar CNNs, we're doing spherical convolutions, and then again now we're doing nonlinear activation functions like ReLU's Pointwise. So for the last part of the talk, before I come on to some numerical examples and problems, is going a bit beyond this kind of standard approach and looking at a more generalized approach and then also a more efficient approach. So this will touch on some of our recent work, but also on a critical earlier piece of work by Condor, which I'll come to in a minute. But really, the point here is we're really going a bit deeper into the study of symmetry, if you like, and really leveraging ideas from group theory, which is really the mathematics of the study of symmetry. And there's actually a lot of connections here with quantum mechanics. We're concerned with rotational symmetry, and remember from Noether's theorem earlier, we said that rotational symmetry was very connected with conservation of angular momentum. And so actually we can leverage a lot of the mechanics and the mathematical machinery of dealing with angular momentum and quantum mechanics and bring that to address additional ways to more accurately encode this rotational equivariance. Because remember, those ReLUs or the pointwise nonlinear activation functions were not strictly rotationally equivariant. So ideally, we'd like to have nonlinear layers that are strictly equivariant. So this was actually developed, again, another seminal work by Condor et al., and basically generalizing some of these previous concepts that we just discussed about spherical CNNs. So basically, again, I wouldn't worry too much about the details, but just to give you, basically, I just want to give you a flavor of some of the ideas behind this, but we're not going to worry too much about the details. But essentially, this starts from generalizing, if you like, spherical signals. And whereas in the past, we considered their Fourier representations F L with a hat, F hat L. And we considered representations on the sphere or the rotation group. Actually, we can consider much more general representations. And we just let this underlying, we add this kind of T index, and we let that to be unconstrained, if you like. And so in the usual setting on the sphere or the rotation group, this is constrained. It's got a particular size and interpretation to a link to a spherical or signal on the rotation group. Here, we allow that to be more general. And that's really the key point of these kind of generalized signals. Because this is still a harmonic representation, we can nevertheless still rotate this efficiently in harmonic space. And this therefore allows us to extend the usual notion of rotational equivariance to these more general spaces. We also need to generalize the notion of convolution. And again, it's, your pretty kind of standard definition of convolution, if you like. But the key point here again is we don't constrain things as much as was considered previously, and now the filter is not constrained to have the same domain as the signal, and so we have two indices, if you like, t and t prime, on the filter across these t, which indexes what are typically called fragments. So this generalized convolution of these generalized signals provides a generalized rotationally equivariant linear operator, which is great. So we've kind of generalized the convolution part of what we were doing before. But critically, we want to consider how to do this nonlinear part. And remember, the previous approach didn't give us something that was strictly equivariant. So here what we're going to do is basically leverage some ideas from group theory and consider what's called the irreducible representations of the rotation group, SO3, which we've seen already, and I'll come on to in a minute, and basically to look at the decomposability of the tensor product between these representations. Now, tensor product is a term that has maybe been a little overused lately, so you might be familiar with TensorFlow, and in TensorFlow we talk about tensors all the time. But in that setting, a tensor is really just like a multi-dimensional array. It's like a multi-dimensional matrix, if you like. Whereas a tensor product really, and tensors generally have a deeper meaning than this. And they relate more to generalizations of the outer products. For example, here we're going to see between vector spaces. So again, I don't want to worry you with the details, but just to give you a flavor of where these results come from, we basically leverage another area of mathematics which links in very closely to group theory called representation theory. And really this is a way of representing abstract algebraic concepts, if you like. So for example, groups by linear transformation. So essentially representing these things by matrices, if you like. So if we consider this tensor product of representation spaces, basically this representation is exactly these big D Wigner matrices that we saw before. So now we want to consider the tensor product of this representation, but which is given as follows. But if you do that, that is not irreducible, which means it cannot be represented by these underlying irreducible elements. So basically, we need to recover what's called an irreducible representation, which essentially corresponds to a kind of change of basis. And in quantum mechanics, this is what's called Cleshth-Gordon theory. And it's really just, so again, don't want you to worry about the details, but again, it's really just telling you how to do this particular change of basis. And this crops up a lot in quantum mechanics when you're considering coupling of angular momenta between states. So this gives us a way now, if you like, to do this tensor product, but still be able to represent things in this underlying space, the harmonic space of SO3. So let's not worry too much about those details. The fundamental point is that this gives us a way to do some kind of nonlinear computation that is also rotationally equivariant. I'm not going to prove that here, but it follows in a relatively straightforward manner. So the key point here is now we have something that can act as these nonlinear activation functions and can also be strictly rotationally equivariant. So this is first considered in neural networks in a paper by Thomas et al. In 2018, and then picked up and leveraged to great effect by Condor et al. In these kind of generalized spherical CNNs. So now all we need to do is consider all pairs of these fragments and collect them together in some kind of generalized signal. Again, this is really just writing out what we discussed. I just want to highlight one point here because we're going to come back to it later, is we want to compute, this is now our nonlinear operator. We want to compute this tensor product and represent it in an irreducible manner. But what we have to compute depends on these indices being within some set. And here we write out this set explicitly. And this kind of follows just by avoiding calculating terms that would otherwise be zero. So this we're going to, again, touch on briefly later. So as I mentioned, this type of approach now should be perfectly equivariant. We can test that numerically, and we have done. And here now we find the mean relative error of these equivariance type tests are again of order floating point machine precision. So indeed, as we expected, effectively strictly rotationally invariant compared to the ReLUs, which around 30–40% error. Okay, so now let me finally come on to a recent work we submitted by Cobb et al. And we now kind of piece together all of these components in a generalized framework. So we consider a general layer of a spherical CNN to have 3 components rather than just 2, a linear part, a nonlinear part, and a linear part. And this allows us to capture other existing frameworks as special cases. So those frameworks of Cohen and Estevez that we saw before have a spherical column, something like a ReLU for a pointwise activation, and then nothing for the third layer. The condor type approach has the identity to start with, but it does this tensor product type activation followed by some kind of generalized convolution. But with this kind of collating all these things together in a general framework means we can now support hybrid models and leverage the advantages of these various approaches alongside each other. And also switch things up a bit by, for example, also including some kind of convolution in this first layer as well. But critically, a significant contribution of this recent work of ours is to construct more efficient layers to be the primary building blocks in this framework, because the current strictly equivariant layers are really prohibitively costly. Basically, the computational cost scales as c squared L to the 5, where c represents some kind of representation capacity and L represents the spatial resolution. So we develop ways to significantly reduce this complexity, but also just make things generally more efficient. So I'm going to go through a couple of things we did there, but again, just very briefly to give you a flavor. So the first thing is we considered a channel-wise structure. So to have a more standard kind of separate channel axis in these CNN type constructions. And that gives us a saving in terms of cost by a factor of k, where k is the number of channels. And that basically represents representational capacity. So again, that gives us a saving from c squared scaling to c. But this channel-wise structure also allows us to consider slightly more constrained types of convolution. So instead of just one general convolution, we have 3 forms of constrained convolutions that follow one another. Firstly, a uniform convolution, which acts across the channels to project down the size of the representation, which can be seen as some kind of learned extension of the nonlinear operator, if you like. And then we have a channel-wise convolution and a cross-channel convolution to learn new features. So this makes a dramatic improvement to both computational, but also parameter efficiently. We can represent things much more efficiently as well. And we also consider how to, another saving by considering that set we saw before and reducing its size. So the nonlinear operator not only needs to inject nonlinearity, but it also needs to perform degree mixing. And actually, it turns out that although typically all possible tensor product-based combinations would be considered, actually that's not necessary. So if we just recall that what we call this P set, PL set, this is size L squared, but actually we can look to reduce this and still capture these kind of interdependencies. So again, without going into too much details, the way we basically do this is we construct a graph representation with the nodes are the L's of interest, but the edges of this graph is specifically this PL set. And really, the motivation is that if we've captured a relationship between, say, 2 L's, L1 and L2, if there's some kind of path between them in that graph. So we don't need to have everything completely connected. We just need to make sure there's paths between these nodes. So basically, we want to select the smallest subgraph to preserve this relationship, which effectively is a minimum spanning tree. So that's what we do. We construct a minimum spanning tree, where we weight the edges by the computational cost. So that basically gives us the most efficient way of preserving these relationships between degrees. And we have this kind of standard minimum spanning tree, which gives us again a saving of L, and making, if we get very good performance with this approach. And we also consider a reduced minimum spanning tree with some logarithmic subsampling, which gives us another saving there. We do notice a small but pretty insignificant performance degradation, but that's more than offset by the computational saving. I'm going to skip this slide. And then finally, we leverage efficient sampling theory on the sphere and rotation group. And as we said before, this gives us access to underlying continuous signal representations and fast ways of computing things like convolutions. And so in particular, we pick up some other previous pieces of work of mine developing sampling theory and fast algorithms to compute harmonic transforms on the sphere and on the rotation group. Okay, so there's a lot of details there. I really just want to give you kind of a flavor of where some of these ideas are coming from. So don't worry too much about the details. For the final couple minutes, I'm just going to touch on some experiments, and we'll see that we actually get state-of-the-art performance on all of these benchmark problems that we consider, both in terms of accuracy, but also in terms of efficiency, in terms of parameter efficiency. So the first problem that has become kind of canonical spherical test problem, if you like, is classifying MNIST digits on the sphere. So, this is not so much a practical problem, but nevertheless a good way to evaluate methods. And we can consider MNIST digits just projected onto the center of the sphere, if you like, or we can also rotate these. This gives us a way of studying these equivariance properties. So this is the network that we consider, this kind of hybrid approach where we start with a couple of layers, which are standard S2 or SO3 comms. We have this other one of these efficient layers where we've got these constrained convolutions, these more efficient tensor product type activations, and again, constrained convolutions, and a couple more of those layers. And so here are the results for classification accuracy for MNIST. So we consider a number of cases. NR means non-rotate, and R is rotate. And this the slash denotes what we do on the training and the test set. So NR means on the training set, we don't rotate, and on the test set, we don't rotate. So in a sense, if the image is, the digit is just at the center of the sphere, this is really like a planar problem, really. And of course, planar networks work pretty well here. So a more interesting case now is if we rotate these digits on the sphere, but we rotate them both in training and when we're testing and evaluating the method. So because planar CNNs don't capture rotational equivariance, they suffer quite a large drop in performance here, 90% classification accuracy as opposed to 99. Basically, you're learning rotations effectively by augmentation. But nevertheless, because you're effectively using the data to do augmentation rather than training the problem at hand, you lose some performance. These are the other spherical CNN type approaches we've considered. And for both of these two problems, essentially with our approach, we more or less recover similar results to the previous state of the art here, which was this Estevez results. But critically, if we look at this third test case, where we don't rotate the data in training, but we do rotate the data in testing. So the model, when it was trained, never saw rotated digits. If you apply planar CNNs here, they're terrible. Remember, there's 10 digits, so we're pretty much almost random because they just have no notion of this rotational equivariance, no notion of what a rotation digit would look like. Whereas the spherical methods, because they have some notion of rotational equivariance, perform very well. And again, here we're basically getting the state of the art now. And because we have this enhanced strictly equivariance layers, we keep equivariance extremely well when we go to this case. And so we see very little drop off in performance, if at all, around standard fluctuations. Let me come to some slightly more practical problems just to finish up. Another problem one can consider is 3D shape classification. So we have some 3D mesh. This could be projected onto a sphere, and then we can use our spherical machine learning methods to classify this and actually also retrieve similar types of shapes. Again, you want rotational equivariance here because no matter how this 3D shape is oriented, it's still the same shape. So you don't want to be sensitive to just the orientation of the shape. Again, we have a architecture which is very similar to before. I think we have an initial axisymmetric convolution layer at the beginning, but otherwise it's very similar. And I won't go into all these metrics in detail, but these are basically precision and recall-based metrics from a standard challenge data set, what's called Shrek 17. And basically, we're getting on 3 of the 5 metrics. We're getting state-of-the-art performance, but critically, if you look at parameter efficiency, we're much more efficient than these alternative methods. And then I'll finish with one final problem, and this is to predict the atomization energy of a molecule. So the energy needed to essentially break up the molecule into its constituent atoms. And these are essentially modeled, each atom is modeled spherically. Given the atom positions and charges, we want to predict the atomization energy. And so again, we want to be invariant to rotations. We also want to be invariant to permutations of the atoms as well. So in this particular model, there's a few more components that are not shown in this architecture diagram to capture kind of permutation equivariance or invariance. But this is the spherical part. And again, it's basically very similar architecture to what we considered before. And here are the results. Cohen and Condor, these are the spherical CNN approaches that also try and tackle this problem. The best result to date is this non-spherical approach by Montavon, and they receive and recover an RMS of about 6. These other spherical methods around 8. We're finding we get an RMS of around 3. So really a significant improvement in performance there. And again, we're also much more efficient in terms of number of parameters. So that's basically all I wanted to talk about. So basically, hopefully, I've highlighted to you the importance of really encoding equivariance to symmetry transformations in deep learning. Really it captures very deep physical properties of underlying generative process. We need to have, in geometric deep learning, we need methods constructed natively on manifolds to really leverage the underlying continuous properties of those types of data. And I briefly reviewed these alternative spherical CNN constructions and just briefly reviewed some of the recent contributions we've made in this area with this general framework, which can capture these other frameworks, support hybrid models, these new efficient layers that are strictly equivariant, and that with this type of approach and leveraging these previous approaches, we're able to achieve state-of-the-art performance, both in terms of accuracy and parameter efficiency. So we had a paper out on this recently, so if you want to know more, you can also go and take a look at that. And finally, I'll just comment that this, as I said, I often have 2 hats, my role in UCL, but also Kaganova. And fundamentally at Kaganova, we're developing deep learning techniques, particularly geometric deep learning techniques, to solve open problems in virtual reality. We're also hiring at the moment, and so please do drop us a line if you're interested, or if you know anyone who also might be interested. If you do that, maybe just mention you've seen this talk, or also feel free to email me directly, because we get a number of emails, and we want to make sure we don't miss those ones that come from people with expertise in AI. So I'll finish up there. Sorry, I realized I went over a little bit, but yeah, just let me know if anyone's got any questions.